Thus far, the nucleophilic substitution reactions we've seen have been mostly at tetrahedral carbon, and the mechanisms that these reactions go by involve SN2, concerted displacement of the leaving group by the nucleophile, or SN1, where the leaving group departs and then the nucleophile comes in. Aromatic compounds substituted with good leaving groups can also participate in nucleophilic substitution reactions, but the conditions are stricter, the reactions are more limited, and the mechanisms are not SN1 and SN2. However, the mechanisms are highly instructive because they apply actually not just in an aromatic context, but also by analogy to a carbonyl context that we'll encounter later when we talk about nucleophilic acyl substitutions. So this nucleophilic aromatic substitution reaction that we'll discuss here is a highly instructive and synthetically valuable process as it allows us to link nucleophiles to aromatic rings rather than electrophiles. It's complementary to electrophilic aromatic substitution in that way. In a nucleophilic aromatic substitution reaction, a nucleophile displaces a good leaving group linked to an aromatic or heteroaromatic ring. This is why we have the word aromatic in there. So, for example, in the sort of prototypical example we see here, we've got sodium hydroxide that contains the hydroxide anion, which is a good nucleophile, and we've got a very electron-deficient aromatic ring here connected to a bromine and an NO2 group. And the bromine in particular is a good leaving group, or nucleophile. It wants to take the pair of electrons in the carbon-bromine bond with it and form bromide, which it does in this reaction. One of the key byproducts is sodium bromide, Na+, Br-. The fact that that carbon highlighted in blue is linked to a good leaving group makes it electrophilic, and the essence of bond formation in nucleophilic aromatic substitution involves linkage between the nucleophilic O of OH- and the electrophilic carbon linked to the bromine. This gives rise to this product not directly, but after a deprotonation of the OH group here by more NaOH, since the product is more acidic than the starting material. The product is a phenol that is more acidic than water. We need to add acid to get to the final neutral phenol product here. But really, the important piece of this is this nucleophilic substitution of the nucleophile hydroxide for a bromide leaving group. This can happen at aromatic carbons, such as benzene carbons, but this does not involve an SN1 or SN2 mechanism. And part of the evidence for this is that there are some pretty significant limitations on nucleophilic aromatic substitutions of benzenes. First and foremost, the ring needs a very, very powerful electron withdrawing group. Typically nitro, and 2 nitros is even better. Electron-poor heteroaromatics also engage in this reaction. Pyridine is a classic example. Those still have to meet condition 2, however, which is that the ring needs to bear a good leaving group. Halides are typical, although sulfonates like tosylate and mesylate can also be used. And for reasons we'll see when we dig into the mechanism, fluoride actually works great in this reaction, even though it's a poor leaving group in SN2 and SN1 reactions. There's a good mechanistic reason for that. The third condition is that the leaving group must be ortho or para with respect to the electron withdrawing group. So for example, we need an ortho bromo nitrobenzene or para bromo nitrobenzene to get this reaction to work. In this example at the bottom of the slide, the nitro group and bromide leaving group are in a meta relationship, and in fact no reaction occurs under the same conditions that led to very facile reaction in the first case. So with that meta relationship, no reaction, but with a para relationship, as we saw up here, reaction goes just fine. And again, there are good mechanistic reasons for this, having to do with the stabilization of negative charge in the reactive intermediate in this mechanism, which is unlike any reactive intermediate that we've seen in a substitution reaction, nucleophilic substitution reaction to this point. It's not a carbocation like we see in SN1, for example. The mechanism of nucleophilic aromatic substitution is not SN1 or SN2. It's a third type of mechanism that we might call associative substitution, to contrast it with the dissociative substitution associated with SN1. In an SN1 reaction, the leaving group dissociates first, and then the nucleophile comes in. But in a nucleophilic aromatic substitution, or SNAR mechanism, the nucleophile comes in first, associates first with the electrophilic carbon, and then the leaving group departs. So it's a two-step mechanism: addition of the nucleophile to the electrophilic carbon, followed by beta elimination of the leaving group. Let's look at the mechanism in detail now with curved arrows and elementary step labels. So here we have our typical para-bromo-nitrobenzene substrate, electrophilic substrate, and hydroxide nucleophile. In the first elementary step of this mechanism, hydroxide adds to the electrophilic carbon, which is the one bearing the leaving group, in what we can call a nucleophilic addition to a polarized pi bond or pi system step, right? This is a very electron deficient aromatic ring thanks to the nitro group, and this is going to land negative charge inside the aromatic ring. This generates a reactive intermediate right here that's known as a Meisenheimer complex, and it contains negative charge within the ring that is delocalized over three different positions, at least three different positions, as we'll see. But the point I want to make first and foremost is that this reactive intermediate is non-aromatic. Addition of the nucleophile has established a tetrahedral carbon inside the ring. So actually, just like electrophilic aromatic substitution, where addition of the electrophile made the ring non-aromatic, addition of a nucleophile also makes the ring non-aromatic. And this has the effect of making that first step of the mechanism very, very uphill in energy. This is universally the rate determining or rate limiting step for SN-AR reactions, addition of the nucleophile, because it destroys aromaticity. Now, despite the destruction of aromaticity, negative charge is still delocalized in this reactive intermediate, and we can start pushing electrons to see where formal negative charge ends up around the ring. And when we do this, and I'll go through it pretty quickly, the first thing I want to point out is that negative charge shows up in ortho positions and the para position with respect to where the nucleophile added. So the nucleophile added here, notice we have negative charge in one ortho position, the other ortho position, and the para position with respect to where that nucleophile added. This is actually why we need a strong electron withdrawing group at the ortho or para position with respect to where the leaving group is located. We need to be able to delocalize that negative charge even more to stabilize this reactive intermediate to make the reaction kinetically plausible to occur at a reasonable timescale. And there's a fourth resonance structure of this particular Meisenheimer complex in which negative charge is actually delocalized into that para nitro group. And it's critical that that nitro group is located at a para position or an ortho position. So I encourage you to pause the video now and make sure that you can see how this resonance structure is derivable from, for example, this resonance form is probably the easiest one to start from. Try pushing electrons from this resonance form to generate this one in which negative charge is located inside the nitro group. And this stabilization is critical. Without that fourth resonance form, this reaction is prohibitively slow. All right, what happens now? Well, to get to the final product, we need to eliminate the bromide leaving group, and that's what happens next through a beta elimination type of step. And the most fancy electron flow we could draw for this is sort of unnecessary, but we could start from this resonance form in which negative charge is located inside the nitro group and push down and through the pi system and kick off bromide by breaking the CBr bond toward bromine. This generates Br minus and reestablishes aromaticity and gets us to the final product. Now, as a brief note here, I've taken a bit of a shortcut. This is going to undergo deprotonation under the reaction conditions because this phenol is quite acidic. It's acidic enough to be deprotonated by hydroxide, and this is why acid needs to be added. This will work for the purposes of illustration, though, of the sort of canonical SN-AR mechanism to sort of ignore that proton transfer. So, beta elimination kicks off bromide. Sodium bromide is a byproduct, right? The sodium cation has been a spectator through all of this, and this reestablishes aromaticity. So this is going to be way, way, way downhill in energy very, very fast after that Meisenheimer complex is generated. So to summarize, we have the first step, nucleophilic addition to a polarized pi bond, polarized because of the electron withdrawing group and the leaving group attached to the electrophilic carbon. The nucleophile adds to the same carbon the leaving group is linked to. And in the second step, beta elimination kicks off the leaving group. This is the canonical mechanism, the typical, the default mode mechanism of nucleophilic aromatic substitution.